Hello, we are Team 12 and we're going to present StarGAN 2 paper. We are going to cover many points today, but we start with introduction. StarGAN 2 tackles image-to-image translations, and there are several problems in the field such that methods should be able to synthesize images with diverse styles in the domain, and they should have scalability over multiple domains. Unfortunately, existing methods address either of the issues, and they can have limited diversity or multiple models for all the domains. StarGAN 2 tackles both and shows significantly improved results. This is an overview of StarGAN 2 consisting of 4 modules. Module A is the generator that translates an input image into an output image, reflecting the domain-specific style code. Module B is the mapping network transforms a latent code into style codes for multiple domains, one of which is randomly selected during training. Module C, the style encoder extracts the style code of an image, allowing the generator to perform reference-guided image synthesis. And finally, Module B, the discriminator distinguishes between real and fake images from multiple domains. For StarGAN replication, that is the previous version of StarGAN 2, I used pre-trained networks that actually saved me a lot of time. There were also no problems related to a model itself, but rather some compatibility issues. There are also 40 domains or attributes that you can apply to an image. I used 3 hair colors, black, blonde, and brown, and also male and old attributes, as you can see in that specific order in the image.
Now I will talk about another comparison paper model, multi-marginal Westerstein GAN and its replication. You can see MWGAN's characteristics compared to StarGAN in this table. They both do not require paired data and can do multi-domain translation tasks without creating multiple individual networks. The difference is that MWGAN can exploit multi-domain correlations and thus expected to have better performance in tasks where data is unbalanced among domains. This difference occurs because MWGAN aims to minimize Westerstein distance among domains. The point is that MWGAN exploits cross-domain or multi-domain correlation, which improves performance. There was a PyTorch implementation of MWGAN on GitHub, so I got test results out of it. The task was trained and tested on Celeb datasets, and total 5 domains were used. The domains are black hair, blonde hair, eyeglasses, mustache, and pale skin. These images in the slide are the sample results. The leftmost image is the source image, which comes from the black hair domain, and each column is the translation result to blonde hair, eyeglasses, mustache, and pale skin domain from left to right. So you can see that in general, it performs quite well.
The source code of StarGAN V2 was well formed, so I didn't need to modify any code during the replication. And it provides various parameters to control the model. During the replication, I encountered 3 major problems. The first one was an environment setting. The second one was a parameter setting to overcome the lack of memory. The last one was a sporadic disconnection of the KVPN. The server that TAs allocated to us had 16 cores, a CPU with 24 GB RAM, and a GeForce RTX 2080 with 12 GB GDRAM. At first, I think this server was good enough to replicate our papers, but there were some limitations to do that. As TA's recommendation, I began to replicate with the Docker and the TensorFlow container images downloaded from the Docker Hub because it could support GPUs and Python 3 well. However, StarGAN V2 was implemented on the PyTorch, so I installed some more required packages using Dockerfile. After that, I could run StarGAN V2, but it didn't work well. because it required the huge RAM to process images. Then with TA's support, I could set the swap partition to compensate for the lack of memory. Unfortunately, the swap partition was not a key to run it because it was too slow. So I had to adjust the parameter for the batch. I tested some values of the batch. Then I found that values less than 10 were good to run it under our environment. In our system, StarGAN V2 took about 2 days to train the model, but for some unknown reason, the KVPN was sporadically disconnected, so I couldn't complete the training at once. But I found the way to resume uncompleted training with resume it parameter, and I shortened the period of saving checkpoint from 10,000 to 1,000 in preparation for the disconnection. Then I continued the training well.
Our goal of improvement was to take multi-marginal Wasserstein distance problem into StarGAN version 2. Multi-marginal Wasserstein distance is simply the weighted sum of output adversarial loss of each generators corresponding to different styles. The original loss term of StarGAN version 2 paper is captured here. LADV means adversarial loss directly associated to performance of generator. LSTY means how much style factor reflected on the generated image. LDS is being maximized to enlarge diversity among generated images for each different styles, and LCYC has information how generator controls reversible factors in images as style well. For adversarial loss term, we will change the value into the result value of calculated multi-marginal Wasserstein distance. For diversification loss, it can relate it to mutual information maximizing loss term in MWGAN, but we will use left one as we keep the base setting of number of styles, which value is 2. It will be shorter in time because left loss do not have to put into discriminator, symbolized pi in the right equation. Further, we will improve the cycle consistency loss term, since it takes value only about the first style. We will simply take mean of each values corresponding to each styles. To make training faster, we will set the epsilon boundary so that we can deal with lower bound term before the value reaches small enough to such epsilon. After it reaches, we will deal with original loss term. At last, in the paper named as in the center, GLO model is the model only differ with the latent value to be spherical, had better performance than each previous backbone. So we plan to make Gaussian prior latent value, having L2 spherical feature for the last improvement.
Our plan is in this table. At week 13, we will finish implementing the improved model and train it and also decide our evaluation method. At week 14, we will test the improved model. At week 15, we will compare the improved model with replication model and prepare for the final presentation and report. Thank you.